Good morning. I am Dr. Anaemon. Presently, I am working with NIET, Greater Noida, as Assistant Professor in Physics. Today, I am going to deliver my lecture on special theory of relativity. But before jumping to that, I would like to explain my subject, that is physics. Usually, we say that it is something that deals with the nature and the natural phenomena. Actually, in physics, we are dealing with the physical laws governing the universe. When we are talking about the physical laws, we are actually dealing with the physical quantities. Now, physical quantities, if we can express, we have to express them in numbers and units. And so we can say that we are actually dealing something with the measurements. And also according to Lord Kelvin, if we can measure something and express it in numbers, then only we know something about that particular quantity. Otherwise, our knowledge is of unsatisfactory kind. So we can say from that in a nutshell that the subject physics is the science of measurements. It was around 1900, some experiments like Michelson-Morley experiment and some other related experiments were done, in which it was found that the age-old classical physics or mechanics couldn't explain them properly. So the emergence of new concept, that is the modern physics, came into existence, and modern physics is mainly comprises of the relativity and the quantum physics. Now when we are talking about the relativity, now in this case what happens, we are actually talking in terms of the entities which are in relation to each other. We can see that rest and motion are relative. To explain this, I will just cite some examples. For example, a teacher is teaching in the classroom. For the students in the classroom are at rest. But for somebody else who is on the moon, for that particular person, students are in motion. As the earth is in motion, so are the students. So we can see that rest and motion are relative. Citing one more example to explain this, I will just take a platform. A person is standing on the platform. Suppose the person is A, and he is observing a train moving with some speed of 150 kilometers per hour. For that person, now two persons A, B and C are standing in the same compartment of the train. For A, B is moving with a velocity of 150 km per hour. But for C, when it is defining B is at rest with respect to him. So for A and C both, we can see that rest and motion are related. Again, when we are talking in terms of the position, I will cite an example. For example, three persons A, B and C are here, and all the three are facing towards me. For A, B is on the left side of him, but for C, B is on the right side of him. And when they have to define, they will speak the position in terms of the left and the right. So we can say that the position here is relative and nothing is absolute here. Also one more thing, when we are talking about in terms of the length, suppose we have three pencils, one is of 1 centimeter. Suppose A pencil is of 1 centimeter, B pencil is of 2 centimeters and C is of 3 centimeters. For C, we can see that B is smaller, and for A, B is larger. So again we can see that the length is relative. From this we can conclude with that in this universe nothing is absolute, everything seems to be relative. And also when we will just move towards the relativity, special theory of relativity especially, we will see that time is also relative. It was Albert Einstein who actually revolutionized and generalized the Newtonian mechanics in new dimensions. Now, this theory of relativity has been categorized into different categories: special theory of relativity and general theory of relativity. When we are talking about the special theory of relativity, we are actually dealing with something that is that two observations or two frames are two different observers in two different frames are at rest with respect to each other or moving with a uniform velocity with respect to each other. Also, one more thing about the special theory of relativity is that we do not incorporate the concept of gravity here. But in case of general theory of relativity, we do take the consideration of the gravity, and also we do talk about the accelerated frames. Now, to make the things more understandable, we have to understand what this frame of reference is. Actually, different observers in different frames of references have different points of view. So, and according to that, we say that nothing in this universe is absolute, everything seems to be relative. Now, coming to this frame of reference, we can just define it like any coordinate system with respect to which we are just defining the position of an object as a function of time. That is known as the frame of reference. So here we are actually having 4 coordinates, 3 for the space x, y, z, and t is the time. Now when we are talking about this frame of reference, it has been categorized into 2 different categories: inertial frame of reference and non-inertial frame of reference. When we are talking about the inertial frame of reference are also termed as unaccelerated frames. Here actually the bodies are at rest with respect to each other, or are moving with a constant or the uniform velocity with respect to each other. Here no external forces come into play, and also the bodies, when we are talking about the inertial frames, here the Newtonian laws of physics and the other laws of physics hold good. We can just cite examples like vehicles moving with uniform velocity as in a straight line as the inertial frame of reference. Now when we are talking about the non-inertial frames are something that are known as accelerated frames. Actually no external force is being applied, even then the body seems to be accelerated, and here actually the fictitious forces come into play. The example of this can be the earth moving around the sun, revolving around the sun, or also something like a rotating merry-go-round. Now a big question usually is asked whether the earth is an inertial frame of reference or not. Strongly according to me, earth is a non-inertial frame of reference. As we can see that earth is revolving around the sun, it is also rotating on its own axis. So we can see that strongly that always a centripetal acceleration is associated with it. So we can strongly say that earth is a non-inertial frame of reference. Also we can see that the earth's surface is not flat, it's curved. So again we have to say that it's a non-inertial frame of reference. But usually for our convenience, sometimes we do say a vehicle that is moving with a uniform velocity in a straight line on the surface, we do take it as a inertial frame, but that is simply for our convenience. And one more thing, when you are talking about the relativity, we do talk about the velocities of 3 into 10 to the power 8 meters per second, and we know that the earth is revolving around the sun with a velocity of 3 into 10 to the power 4 meters per second. So sometimes we do ignore the effect of this centripetal acceleration, and for our convenience we do take it as inertial frame, but strongly we have to say that it's a non-inertial frame of reference. To understand this transformation equation, I will just first of all take the example from the Galilean transformation. Galilean transformation is actually based on the age-old classical physics. It has nothing to do with the relativity part yet. To just understand it, or we can just conceive it by taking a frame, for example railway station or the railway track, especially railway track on which the train is initially present. Now this railway track, we have to just think that it is a frame which will be always stationary, which will be at rest, and the train, suppose this frame now S dash, I am just talking about that train is S dash frame. Now after some time t, it starts moving along the x direction. Now we can see, since there is change only in the x direction, y and z do not change here. This after some time t, what happens? The observer on the railway track and some observer in the compartment of the train, or we can see that the frame S dash, both these observers are observing an event at the point P, suppose, For the observer O, the coordinates x, y, z and t. That's 4 coordinates in terms of the space and the time. For observer O, the coordinates are x, y, z and t. But for the observer O dash, who is also observing the event, the coordinates are x dash, y dash, z dash and t dash. But in classical concept, we do know that whatever the time is being observed by an observer who is on the railway track will be the same as that of the person who is staying in the compartment of the train. So here we can say that time t is equal to t dash, no issues about this. Now when we are talking about this observer O, we can see that the distance from this to this point P is x, but for this observer O dash, the distance from O dash to P is x dash. Now when we have to correlate the observations of these two, we can see that x dash will be equal to x minus vt. What vt is? V is the velocity. That velocity is constant velocity with which frame s dash is moving, and time taken by it is t. So the distance from this to this will be v into t. Now in this case, x dash will be equal to x minus vt. Let it be equation number 1. And since there is no change in the y and z coordinates, since the train or this frame s dash, for frame s dash is moving only along x direction, so there is only change in x. So rest of the coordinates, that is y and z, will remain the same. Also from age or classical concepts, we have the time t dash equal to t, so let it be equation number 4. To understand the velocity now, what we will do, we will just differentiate equation 1 with respect to itself, then dx dash will be equal to dx minus v into dt. Since we know that v is constant, that's why. Now if we, from these equations again, if we will just solve and differentiate them as well, then we will see that dy dash will be equal to dy, then dz dash will be equal to dz, and dt dash will be equal to dt. Now just naming it like this is as 5, let it be 6, let it be 7, let it be 8. Now dt dash is equal to dt, no issues. Now we will divide both sides. Suppose with by dt dash, then it will become equal to dx by dt dash minus v dt by dt dash. But we know from equation 8, from equation 8 we have dt dash equal to dt. So we can also write this equation as dx dash by dt dash. It's okay for dx and x dash and d dash because they are in the same frame according to the same observer. So we can also say that dx by dt, since the dt dash is equal to dt. Now v dt upon dt, instead of dt dash I can take dt and both will cancel out. We will have here the velocity component v. Now we know that rate of change of the position with respect to time gives us what? That's known as the velocity. So since we have taken this as for the frame s dash, we have taken the coordinates as in terms of x dash, y dash, z dash and t dash. So the velocity component we will take in terms of u dash. The velocity component here, dx dash by dt dash is equal to u dash. The dx by dt will be u and velocity v will be. One important observation here, we can see that u dash is not equal to u. U dash is not equal to u, because we can see that u dash is equal to u minus v. So we can say that velocity is not invariant. That means not invariant, double negative means positive, that it is variant. Now when we are talking in terms of acceleration, we have to differentiate this equation again with respect to time. Then it will become equal to du dash by dt dash, that will be equal to du by dt minus v. Since v is constant, so the differentiation of that will be equal to 0. So here we can see that the acceleration, since the rate of change of velocity gives us the acceleration, and that is equal to a dash is equal to a. A dash is equal to Okay, that means the acceleration here is not changing, it is not variant. Now from this we can just conclude that from the Galilean transformation or from the age-old classical concept, we can see that the velocity is variant but the acceleration is not variant. That means it is unchanging, it remains the same. So we can say we are just actually talking about the unaccelerated frames here.